Pi is frequently approximated using values like 3.14 or 22/7. However, these are just rational approximations. In reality, pi is an irrational number. Its decimal expansion is infinite and never repeats. We can prove this property formally using a very specific construction involving an integral. We will utilize a proof by contradiction. We begin by assuming the opposite of what we want to prove, that pi is a rational number, which can be expressed as a fraction, a/b, where a and b are both integers. If this assumption leads to a contradiction, it follows that pi is irrational. This proof relies on an integral that must be an integer while also being bounded between 0 and 1. To start the proof, we define a specific polynomial function based on the assumption that pi is rational. This function is denoted as f of x. Here is the formal definition of our polynomial. The key property we must verify involves its derivatives. We must show that all derivatives of this function at both 0 and pi evaluate to integer values. Expanding the numerator reveals that the lowest power of x in the sum is n. Every coefficient in this expansion is an integer, provided that a and b are integers. Because every term in the summation has an exponent of at least n, the behavior of the derivatives at 0 is strictly defined. Now, let's examine the derivatives of our function at x equals 0. When we take the kth derivative of a power x to the j and evaluate at 0, the result is only non-zero when j equals k. Applying this rule, the kth derivative of our function simplifies nicely. The result is a constant multiplied by k factorial divided by n factorial. Since k is at least n, this ratio is an integer, guaranteeing that all derivatives at 0 are integers. Having established the integer result at 0, we now evaluate the derivatives at pi. The function f of x possesses a beautiful symmetry property. Let's formally verify this by substituting pi minus x into our function. First, we expand the inner expression by distributing the b. Next, we use our rational assumption to replace pi with a/b, noting that a minus b pi is 0. Finding a common denominator for the first term allows b to the power of n to cancel out. This simplifies exactly back to our original function, proving the symmetry. Due to this exact symmetry, the derivatives at pi must also be integers. Both boundary conditions are now fully established. We now evaluate the integral I sub n, defined as the integral from 0 to pi of our function f of x multiplied by sine of x. To solve this, we will apply the technique of integration by parts. This will reveal a recursive pattern in the derivatives of f of x. An initial application of integration by parts allows us to expand the integral. By setting u equal to f of x and dv equal to sine x dx, we compute the differential du and the integral v. This transforms our integral into a boundary term and a new integral term. Applying integration by parts a second time reveals the iterative behavior. This time, we differentiate f prime to get f double prime, and we integrate the cosine term to recover sine. The result is a consolidated expression for I sub n after 2 cycles. Continuing this process indefinitely, the integral is reduced to a compact boundary evaluation. We define a function f of x as the alternating sum of the even-ordered derivatives of f of x. This allows us to write the entire analytical expansion in a single, simple form. We now evaluate this expression at the limits of 0 and pi. Substituting the boundaries, we expand the analytical form. Notice that every term containing sine evaluates to 0, and with cosine of pi being -1, the terms simplify significantly. Applying these limits, we are left with a simple sum of f at pi and f at 0. We previously proved that f of x and its derivatives are all integers at these boundaries. Therefore, f of 0 and f of pi are also integers. This leads us to a critical conclusion. The integral I sub n must be an integer. Furthermore, because the integrand is positive, I sub n must be at least 1. We now establish an upper bound for the integral. Since sin x is bounded by 1 on the interval from 0 to pi, we replace it with its maximum value in the integrand. This simplifies our integral into an inequality. By choosing n to be large, we can further bound the polynomial part of our function f of x. Recall that m is the maximum value of the polynomial part, allowing us to bound f of x by this fraction. Integrating this constant across the entire interval yields an upper bound of pi times m to the power n over n factorial. Crucially, the factorial function grows much faster than any exponential growth from m to the power n. Because this upper bound approaches 0, it follows that for a sufficiently large value of n, our integral I sub n must be strictly bounded within the open interval from 0 to 1. However, recall our earlier result. I sub n must be a positive integer. Since there are no integers between 0 and 1, we have reached a direct logical contradiction. We now analyze the contradiction derived from our results. We have established two conflicting properties for I sub n. Our calculus derivation proved that I sub n must be an integer greater than or equal to 1. However, our bounding analysis proved that I sub n must be strictly between 0 and 1. It is mathematically impossible for both conditions to be satisfied simultaneously. Given that no integers exist within the open interval from 0 to 1, we reached a formal contradiction. This confirms that our initial assumption, that pi is rational, is incorrect. We have formally proven that pi is irrational. This property is a fundamental result in number theory. The proof follows the formal methodology of contradiction. Subscribe to Mathilda's Math Lab for more technical content. I'm Mathilda. Thank you for watching. Until next time.